material removal. That's the reason machining processes is also called material removal processes. And it covers the following broad categories. First one is carding. Carding is the traditional carding, or traditional material carding. Involves single point. Single point we know is a turning is a single point, right? So we speak we just say it is a single point because we have a tool tape and we have a workpiece. This is for turning. Or multi-point cutting tools. Multi-point, this one is a drilling and also this is a milling. And they are multi-point cutting tools. Multi-point, single point means that how many points we have between the workpiece and the tool. Such as turning is a single point. The boring, drilling, taping, milling, sawing, and brushing, and they are multi-point. The turning is the most important, is the fundamental machining processes. So principally, in principle, all these they are built upon this turning. The second category is abrasive processes. Abrasive processes means that we use abrasives and to remove this material from the raw, to remove the material from the raw material to build this final product. For example, this grinding, coiling, lashing, and ultrasonic machining. Ultrasonic machining is using ultrasonic to machine. So the third one is advanced machining processes, which use the electrical, chemical, thermal, and hydrodynamic and optical source of energy, as well as combination of these energy source to remove material from the workpiece surface. I just told you three advanced manufacturing processes that I will cover. They include this is laser machining. Laser machining is use the heat. Okay, use the heat. Also EDM. EDM is electrical discharge machining. Is also using the heat because we have electrode, and so there is a discharge, and the high heat, high amount of heat can melt the material, and then the electrical fluid will flush them away. So we can get our final product. So both the EDM and laser, they are using the heat, the thermal. They are using thermal. So this is another additive manufacturing. Some additive manufacturing, they also use the thermal, right, to melt things selectively. So there is also chemical machining. Just they want these chemical things or electrical things, and to just remove the material, remove some part of material from the raw material. So this is the advanced manufacturing processes. We are going to cover laser machining, EDM, along with the additive manufacturing in detail. So this is for other material processes, and I can just give you some handouts, and you can just review. Right? So these are three categories: carding, abrasive processes, and advanced machining processes. So what are the advantages of the machining processes? So why? Because it is time-consuming, energy demanding, and also very, very expensive. And why we want to use machining instead of other things, casting or this kind of all this forming. The first, closer dimensional accuracy. So closer, we can using the machining, we can get a closer dimensional accuracy. Maybe required than is achievable from other metalworking processes alone. For example, in a forged crack shaft, the bearing surface and the holes cannot be produced with two-dimensional accuracy and surface finish by forming and shaping processes alone. So we can get much better dimensional accuracy. So this is the first advantage of this machining over this metal forming or shaping, this kind of thing. The second one, the parts may possess external and internal geometric features such as sharp corners and internal threads that cannot be produced by forming and shaping processes. Right? If we have internal things, internal features. It's very, very difficult to get this is internal features, and also with this is a very, very high accuracy and by forming and shaping. But this is very difficult. The third one is some parts are heat treated for improved hardness and wear resistance, and these heat treated parts may undergo distortion and surface discoloration, and they generally require additional and finishing operations. Additional finishing operations here, and usually we have using this machining and to remove the oxide layer or other discoloration or this kind of things. The fourth one is a special surface characteristics or textures may be required on all or selected area of workpiece surfaces of the product that cannot be produced by other means. For example, engine blocks, for example, have regions that must possess far better surface finish and dimensional accuracy than other regions. Also, the copper mirrors, so this mirror, right, with very, very high reflectivity, for example, are made by machining with a diamond cutting tool. So otherwise, you cannot get that high quality. This is the copper mirrors. So the last one is it may be more economical to machine the parts than to manufacture it by other processes, particularly if the number of parts required is very, very small. Right? I recall that metalworking processes typically require expensive dies and tooling, and the cost of which can only be justified if the number of parts made is high enough. So this is for small amount of products. It is much better to use this is a machining instead of this metal forming, because you usually to have very, very expensive dies and tooling. So this is several advantages of machining processes. So everything has two sides: advantages over other things, and some limitations. There are other limitations of machining processes. And first limitation is that machining process itself is inevitably with the material. This is understandable, right? Because you are going to remove layers of the material from workpiece, and just become the chips. The chips are useless. No, I'm sorry. I should not say that. The chips, the metallurgical properties are changed, right? So mechanical properties are changed. And usually, in the machine shop, usually the chips, they are just collected as almost trash, right? Sometimes we can recycle it, but it does not have too much value. So this is one thing. Generally require more energy and labor than other metalworking operations, because we need to use the tool to cut layers of materials from the raw material, and there is a lot of energy on labor are required. So thus, machining should be avoided or minimized whenever possible. Right? So this one you need to keep this in mind. And second one is that removing a volume of material from workpiece generally takes more time than other processes. This is time consuming. The third one, unless carried out properly, material removal processes can have adverse effects on the surface integrity of the product, including particularly white. Can somebody imagine why?
Well, you could destroy like the material as like a hardened surface. You could destroy it because hardening and stuff.
Yeah, okay. So because when we cut material using a tool, usually and the high temperature, we will this cutting will result in very, very high temperature as this is intact, as this contact area. So as a result, the metallurgical properties of the workpiece will be changed. That area is called heat affected zones. It's called HAZ, heat affected zones. Heat affected zone. So not just the machining, laser for this traditional machining, laser machining, EDM, both of them, they have this kind of problem, HAZ. If HAZ, how to minimize the HAZ, the layer of heat affected zone, that is one of the research tasks. Okay? If this surface integrity is changed, and usually they just get the very bad is a fatigue line, some cracks. You may have some existing cracks already. So this is here are the three limitations for traditional machining processes. Any questions regarding this slide? Advantages and disadvantages. We call limitation. Questions? No question? So here is a machining system, and this is a lathe. This is a typical lathe, right? I think you are familiar with this kind of lathe. And this kind of machine we call machine tool, right? This machine tool is this lathe or milling. So this is called machine tool. Consists of workpiece, cutting tool, and tool holder, and workpiece holding a device and the machine tool. The whole body is called machine tool. See, and we have this is the tool post. We have this compound. This is a rest. This is a carriage. So this is a ways to move this. This is called this is a handle wheel. Also, this is called bed. Usually, this is workpiece is called here. Right? So this is I think you are very familiar with this one, right? So who has not taken the machine shop class? Let me know. You have not? Okay. All other students have already taken, right? Okay, great. So then we learned the chip and how the chip forms. Mechanics of chip formation. For this is a turning. This is the typical turning, and we have this is a cylindrical bar. This is cylindrical bar. So this is the final dimension, and this is the initial dimension, and this is a tool. Our tool is moving, and we call this even though this is multiple microscopically, this is a line contact area, but we still call this one as a single point as a contact. Okay, that's the tool tape. So here, this is a speed turning. As you can see, is a speed turning. A second one is this is a tool. This is a tool. This is my tool is cutting radially. So this part will become thinner, and finally, this part disappears, and then this guy will fall. Right? So this is cutting off. And the third one is the slab milling. The slab milling, this is milling. Milling, they have multiple cutting edges. When this tool is in the contact with this workpiece. So now here you can see, and this cutter is not straight. This is oriented. This is oriented at an angle. It's not straight. So here is the end mill. This end milling. End milling, and we can just cut a very complex features. So turning cannot do it. Turning usually we do use the turning to machine the cylindrical workpiece. But that's the reason the milling is more versatile than this is the turning. So this is orthogonal cutting. What is orthogonal cutting? What is orthogonal cutting? Do you know? Have you guys ever heard orthogonal cutting? Okay. Orthogonal cutting, you can see. So this is orthogonal cutting, and this is a tool. Right? This is my tool, and so here is a workpiece, and so here's a chip. So orthogonal cutting means that my tool is cutting the whole thickness of the workpiece. Actually, this is not the case. This is just the idealized case. Idealized case is that the machine, this tool, is cutting the whole thickness of the workpiece. This is orthogonal cutting. But actually, no. Actually, here is my cylindrical workpiece. When I cut it, right? When I cut it, my tool is in the contact with this one, and also on the shoulder, and my tool is in contact with my workpiece at other location. That is normal. That is 3D cutting. So this is orthogonal cutting with 2D cutting. Okay. There are several important concepts. I'm going to go through these. So here is a tool, right? Here is a tool. Here is a vertical, and here is a vertical line. It's a vertical line. So here is my tool surface, and so this is my cutting speed. This is my the speed, the cutting speed. So this angle, right? So angle between the rig face, I call this is a rig face. This is a rig face. A rig face is a tool space. Is a tool space that is in contact with the tape for the rig face. Rig face. And this rig face is the face on which the tool is in contact with the tape. This is the rig face. So this angle is called rig angle alpha. Rig angle alpha. And you can see the rig angle alpha, if alpha is bigger, the tool is sharper. Remember, this alpha is angle between the rig face and your vertical line, and this vertical line. If this alpha is bigger, my tool is sharper. Right? So this alpha can be positive. Alpha can be positive and can be negative. Negative is, that means it goes in another way. So this is rig face, rig angle, a very, very important concept, right? So here, rig angle is a rig angle, this is a tool. And here, okay, here is a flank face, flank face of the tool. This is a flank face. Right? And then here is the angle. The angle is called a relief angle. Relief angle. Or the clearance angle. Or this is a clearance angle. So the relief angle and the clearance angle is the angle formed by the flank face and the machine surface. Right now. In our midterm, I might give you a picture, ask you to label all these things. Right? So clearance angle or relief angle is the angle between the face, flank face of the tool and the machine surface of the workpiece. So these are called alpha, this is called beta. So we also have shear angle. This is the shear angle, and shear angle phi. The shear angle phi. This is shear angle phi. So this is very, very important. So this is idealized case. Okay, usually in reality, so here we don't have a single point here. And single edge, we have a curve instead. But for the idealized case, and so this is the shear angle. And T0 is uncaught tape thickness. So this is T0 is called uncaught tape thickness. T0. So this is machine surface, right? So this one is a curve. This I told you is in reality So here is a curve instead of single edge. Here's a curve of the surface. This is the uncolored tip thickness. And you should also know that if the alpha is positive, that means your tool is sharp. However, if your alpha goes in this way negative, that means your tool is dull. Does that make sense? Okay, so this is my cutting speed. So here is my vertical line. If my tool goes this way, my alpha is positive. If my tool goes this way, my alpha is negative. Negative tool, you can see very clearly, if we have negative weak angle, and the tool is mainly compressing the workpiece, right? However, if we have a sharp angle, that means the alpha is positive, it is cutting. Questions, comments, remarks? So here, see the beam as orthogonal cutting without a well-defined shear plane. So this is usually much closer to the reality. This is idealized case. Questions regarding this tool? So here TC is the chip thickness. TC is the chip thickness. Any questions? So here is a mechanics of chip formation in the cutting process. The major independent variables. Okay, I'm talking about independent variables. That is the variables that you can control and change and control directly. And they are the type of cutting tool and its condition. What kind of tool you are using, and tool shape, and surface finish, and its sharpness. This is surface finish about the tool shape or the tool. The workpiece material and its condition, along with the temperature at which it is operating the temperature. The next one is the cutting conditions such as cutting speed and feeder rate and the depth cut. Write down it. So this is three very, very important the cutting conditions. Cutting speed. I want to write down. Right? Cutting speed and feed is also called feeder rate, RATE, and this is depth cut. And then type of cutting fluids. If this is dry cutting, or this is you have some coolant, or you have some how the coolant is applied. If you immerse, this is a workpiece in the coolant, or you can just use the minimum quality cooling conditions. The characteristics of machine tool this is a big machine tool. Particularly is stiffness and damping. The stiffness and damping is very important. Last one is the tool holders. Okay? What kind of tool holders are you using? And workpiece holding, and fixing devices. Well, a question? What's the difference between the speed and the feed? The speed is the cutting speed, the relative motion between the workpiece and the tool. Okay? And the feed? And the feed is how far you move. So for example, so this is my turning, right? This is my cylindrical workpiece, and my thumb now behaves like a tool, right? The workpiece, the cutting speed is how fast my cylindrical workpiece is rotating. And for here, I can get this linear speed, right? Linear speed, how fast this guy is rotating. The feeder rate means that and how fast my tool is moving longitudinally. So this way. If you have operated this lathe, and you should know that, right? So this way is rotating spindle speed and resulting in the affects the cutting speed, and how fast my tool is moving in this direction. That is the feeder rate. And depth cut means that visually and how much I feed, how much I move is radially. That is the depth of curve. Question? I want you to know, okay? Speed, and depth curve. If you have an interval with someone, if they ask you what are the typical cutting conditions, you should know that. So dependent variables, that means they are dependent upon what we just talked about, other independent variables somehow, somewhat. So for example, the type of chip produced. The type of chip depends upon your material or workpiece, depends on the operational temperature, and depends on how big, how sharp your tool is, depends on all those things. That's the reason this guy is called dependent variable. And second one is the force required and energy dissipated in the cutting process. Definitely these two guys, and they are dependent variables, and they are dependent upon your workpiece, your tool, and also the cutting conditions, and also this is whether you have fluid, you have the coolant or not. This is the cooling, if we have cooling mechanism or not. The temperature rise in the workpiece, the chip, and the tool, and this also dependable. Where the tool wear, the chipping of the tool, and failure of the tool, and definitely it is affected by the previous independent variables. And surface finish and integrity of the workpiece of this machine. So this is the dependent. You have no control directly, okay? You have no control directly, and they just dependent upon under the cutting conditions, the tool, the workpiece material, the tool material, and the how sharp your tool is, and other independent variables. And then we talk about this is orthogonal cutting chip formation. So here is a chip. So here is our tool, and for exaggeration, we just have treat this one as different layers of the tool, right? So this is our shear angle phi, is our workpiece. So this is alpha. So this is my vertical line. So this is my river face. So this you can see this tool has positive alpha. That means it's sharp tool. This is my tool. So here, let's go here. We have CBA. We just exaggerate this one. So here is our velocity. So this velocity is a relative motion between the tool and the chip. Right? But in reality, for our turning, the workpiece is moving, the tool is fixed. Do you agree? But this is still the relative motion. So this is the speed. So this is the speed. I can just say my workpiece is fixed here. My tool is moving. It does not matter, right? So just relative motion. So here is my V velocity. This is my cutting speed. So this is Vs. Vs is the speed along the shear plane. So this one, right? So this one is the velocity of the speed of the chip. How fast the chip is moving along this rift face. So this angle, we have this angle. So this is phi, and this is alpha. So this angle is alpha. So this is my tool, right? So this is my chip speed. The chip's speed is parallel to your rift face, right? You agree? So that's the reason. So here is my alpha. And so these three speeds, and they form a triangle of the speed triangle. So this is alpha. So this angle will be 90 degrees minus alpha. We know that these three angles, the sum of these three angles equals 180, right? And so we can get this angle, which equals 90 degrees minus phi minus alpha. So phi is dependent upon your cutting conditions, your workpiece. Phi, alpha, you can control alpha. Alpha is an independent variable. However, phi is not an independent variable. Phi is dependent upon the workpiece material, the cutting conditions. So but based on this one, this is the speed triangle, and we can solve if we know the V, we can calculate the Vx and Vc. Do you agree? We use the sine theorem, sine equation. You still remember the sine equation? Huh? You still remember, right? So phi, okay? So this is a phi. Phi corresponds to Vc. Do you agree? Vc is divided by this, I'm sorry. So this is V, right? So this is V, and this V is corresponding to 90 degree minus phi plus alpha. Right? Do you still remember what is the sine theorem for the trigonometry? Huh? Yeah.
Oh, do you want me to answer it, or was that just
Yeah, I'm asking a question. What is the sine function? What is the sine the theorem?
is it just the ratio of each angle to the corresponding opposite side?
Yeah.
You equal them all together, solve for something.
Yeah. Okay. For our case, let me show you.
So that's sine A.
Yeah. Yes. Okay. For our case, my V, okay? My V corresponds to this alpha, right? So that means my V sine phi, not sorry, 90 degree minus phi plus alpha. Do you agree? And this equals my Vs divided by sine 90 degree minus alpha. This equals my third one. Third one is Vc, and Vc divided by sine phi. Do you agree? Okay, and then we know that this is sine, cosine, cosine. This one equals V. We will change this one as cosine phi minus alpha to form this term. And second term here equals cosine alpha. Sine phi. Right? Cosine. Here's the cosine.
Last one's a sine.
So this is sine now. Itself is sine.
Is it sine phi or sine?
Sine phi, I'm sorry.
Sine one?
Sine phi, sine phi. VC. VC corresponds to phi, yes. VC corresponds to phi. Vs corresponds 90 degree minus alpha. And this V corresponds to this one. Sine. Sine means phi. Sine becomes cosine phi minus alpha. I'm sorry, here. So this is equation. So here is this is not alpha. Okay, this is phi. So this is equation I got from the textbook. This is not correct. Any questions? Any questions? So Vs the velocity at which shearing takes place in the shear plane in that direction. The spin rate, there is another concept. The shear spin rate is the ratio of Vs divided by 2 the thickness. Vs, this is thickness, we say A. Next thing, thickness A. So experimental evidence indicates that this A is typically on order of 10 minus 2 millimeter to 10 minus 3 millimeter. This range indicates that at a low temperature, low starting speed, the spin rate is very, very high. Right? So what I want you to know is that this equation. Who figured this out? Thank you. Right? So I did not notice that this. Right. I got this one from textbook. Thank you. Any questions? If there is no question, let me summarize a little bit. This is especially I want you to know these concepts. For the orthogonal carding, and we talk about the rig phase, rig angle, blank phase. We call this relief angle, or sometimes people call the blank angle also. Whenever you hear this, and don't panic. Relief angle or clearance angle. We also learn the shear angle. Okay, shear angle. T0 is uncarved chip thickness, and TC is the chip thickness. And then finally, we learn the relationship between the cutting speed and the shearing speed along the shear plane, and also the chip speed. And how we define this one, and we use the sine theorem that we have learned in the trigonometry. So remember this equation. Without any questions, I'm going to enter to this session. So these concepts are very, very important.